All right, once you are done with your daily Q and you have your study guide out, we're going to get started. I'm going to start with chapter 1. I'm going to go through 1, 2, and 3 at minimum today. If we get done with 3 early, which I anticipate we will go through 4. We'll start with 5. As far as I can get till the bell rings is how I'm going to work through this. If you have questions as we're going through, you need to make sure you're referencing your study guide. If there's something that's not checked off, or there's a problem you want me to go over, there's an equation you want me to talk about, if there's something you want me to talk about more, you have to ask. Okay, that's how this works. All right, so I'm going to start with chapter 1. Chapter 1 involved metric prefixes, kilo, milli, centi, deci, those kinds of things. Remember that there are some that you have to have memorized. Kilo is one of the most commonly used ones that we have used. Milli is another one that we have used a lot. Centi is more of a physics thing, but I digress. Same type of issue. There are some of the very, very small ones, micro and nano. Those are all different prefixes that are things that will come up again at some point. Maybe not on your final exam, but you will need to know them. Okay? Dimensional analysis and calculations. So if I ask you to convert 1 hour to seconds, can you do that? Yeah. Yes, you can. If I ask you to convert moles to grams, can you do that? Yes. Thank you. I appreciate it. That's more of a chapter 3 thing, but just putting it out there. Sig figs, scientific notation, SI units. So the SI units are the common units used in sciences. For temperature, what's the SI unit? Kelvin, or we also see Celsius a lot in our experiments. We don't have thermometers that read Kelvin. We have thermometers that read Celsius. Converting from Celsius to Kelvin is something we should all be pretty comfortable doing. You just add 273 to go from Celsius to Kelvin. All right. SI unit for volume. Liters. Okay. What other type of volume do we typically see? Milliliters. Okay. Length. Meter. So meters, centimeters, all of those different prefixes do apply. What about energy? Joules. Capital J for joules. I don't think we had to talk about force in this class, but anybody know the unit for force would be the capital N Newton. All right. What else? What other types of SI units am I missing?
Atomic pressure. Sorry, atmospheric pressure.
Oh, pressure, yeah. ATM. Remember that pressure, we learned a lot of different pressure units, but ATM is the SI unit. Good idea. All right. Elements, compounds, and mixtures. Hopefully we feel pretty confident about that. Is there anything in chapter 1 I need to go over? No questions? Raise your hand. Forever hold peace. Okay. Moving on to chapter 2, atomic structure. Ions, ionic compounds, some basics behind that. Whew. Dalton's atomic theory, the nuclear model of the atom. What's in the middle of an atom?
Nucleus.
Of the nucleus, good. Okay. What's in the nucleus? Protons and neutrons, more specifically. What's outside of the nucleus?
Electrons.
The electrons. One of these things takes up more space than the other, and it's the electrons. We call it the electron cloud for a reason. They're moving really fast. They take up a lot of space. 99% of the space in an atom is taken up by that electron cloud. Okay, some of the basics that we learned last year. What other types of things in chapter 2 do we have questions over? There was some naming things. Have we really done a lot of naming? No. Are you still responsible for kind of understanding the polyatomic ion sulfate is SO4 with a 2- charge? Absolutely, because we've done stuff with that all semester. Those kinds of things. Yes, Carly?
What are the basic postulates?
Basic postulates of Dalton's atomic theory? His 5 postulates. 1 or 2 of which were wrong. Do you have to have them memorized? Oh, that's a good question. What I would memorize is the ones that are wrong. The ones that were adjusted are the ones I would memorize.
All right.
The other 3 you do not need to have committed to memory because you already do. All right, give me 1 second. I'll find them for you. All right. First one, in a given compound, the relative numbers and kinds of atoms are constant. So, CO2 will always have 1 carbon and 2 oxygens, is what that means. The total mass of materials present after a chemical reaction is the same as the total mass present before the reaction, also known as the conservation of mass. Is that still true? Yes, that one didn't go away. If 2 elements A and B combine to form more than 1 compound, the masses of B that can combine with a given mass of A are in the ratio of small whole numbers. This is why we can't have C1.503. Okay, this is why we do not get half atoms in our compounds. All right, another one was that it was like so it says each element is composed of the smallest indivisible thing called an atom. Technically, are atoms divisible?
Yes.
Yeah. So he said that the smallest particle was the atom, and really the smallest particles are even smaller than protons, neutrons, and electrons. Okay, so that was one of his ones that was wrong. One of the things he said was all atoms of a given element are identical, but one element's atoms are going to be different than another element's. So this is why we have nitrogen atoms that are different than oxygen atoms. Okay, that's the second one. Okay, so another one of his is that you cannot change atoms of one element into atoms of a different element by chemical reactions. In other words, he said atoms cannot be created or destroyed from nothing. Okay. Now, can atoms actually change from one element to another? Yes, they can. It's called nuclear chemistry. So he's right, but only kinda on that one. Okay. The big one to remember is that he said that atoms are the smallest unit. That's not correct. We know that they can be subdivided. Okay. Any other questions from chapter 2? Go ahead, Shelby.
Empirical formula.
Empirical formula is a good question. So what is an empirical formula? So it's the smallest unit of a formula that can exist. So if I subdivided all of this as small as I could, this would be like the ratio of every type of element within this specific type of compound. Now, an empirical formula tells us this is the smallest version of something that can be simplified. But this is like the real compound. This is just the smallest version of that compound that can exist. Can other multiples exist of this particular formula? Absolutely. Could we have C3H6O3? We could. Okay. So the empirical formula is this one, and this is what we call a molecular formula. Am I going to ask you to do an empirical formula calculation on your final exam? Heck no.
Thank you.
First off, there's a lot of other things I'd rather you do on your final exam that you prove to me that you didn't do in honors chemistry. Yes?
Are there not going to be a lot of questions on like 1, 2, and 3?
1, 2, and 3 usually get like maybe 4 or 5 multiple choice questions. It's not too intense. Very little math, if any. The math you'll be asked to do are things like how many protons, neutrons, and electrons are there in this atom?
Yeah, that's pretty complicated.
Or, or you may be asked to do stoichiometry, just very basic stoichiometry. But a lot of times those kinds of questions can be incorporated into questions from later chapters, right? If I give you a question in chapter 4 that asks you to do some kind of molecular mass and then a conversion from moles to grams or from grams to moles first, that covers the concept from chapter 3. Yes.
So it's mostly like theory stuff. That's
Yeah. Mostly the more conceptual stuff from chapters 1, 2, and 3.
So should we know like all of the atomic theory?
Like I said, I would focus on the one that's wrong, or like the 2 that are wrong.
Is that going to be the case for like every chapter like
No, you're going to be doing math on your phone.
Okay, good.
I can incorporate your math into Canvas. You've seen that before. On quizzes, I've had like, hey, do this, and then,
Okay,
yeah.
that's the stuff that I actually understand.
Fair. All right. Anything else from chapter 2? Move on to chapter 3. So we've got a few different concepts in chapter 3. Some of the more mathematical heavy stuff that we learn in honors chem, including limiting reactants, stoichiometry, so moving from moles to grams or grams to moles, the concept behind Avogadro's number, and how Avogadro's number of atoms is 1 mole, and converting from atoms to moles or moles to atoms, or converting from atoms all the way to grams by going through the mole, things of that nature. There were the different types of reactions in chapter 3. We'll start the writing part of this. So types of reactions, remember some of them? combination, also known as a synthesis reaction. What other types of reactions? Decom. Where we break something apart. Do A and B have to be individual elements? No. Can they be polyatomic ions? Yes, they could. All right. What else? Ooh, displacement. There's two types of displacement reactions. Yep. Ooh, no, it's like AX plus. And then there's the other type of single displacement, which is like you either have the displacement of the cation or you have the displacement of the anion. Depends. Double displacement. Everything changes place. Last but certainly not least, combustion. Is that guy? Remember the X and Y can be any number in those? Hydrocarbon is the minimum. Could this also end up having an oxygen on it? Yes. Okay. So the different types of compounds, yep.
Combustion technically be a decomp reaction if it's just one molecule or compound going into CO2 or H2O?
It has to have oxygen in order to be combustion. All right, so that's that one. Calculating formula weights, so molar masses. Yes?
The percentage competition, limiting reactions to percentage yield.
Yep. So, can I erase? Are we good? Say that we're asked to figure out what percent of this particular molecule is actually made up of just carbon. What we're going to do is we're going to measure the total mass of carbon. Over the molar mass of the whole thing. Multiply by 100%. Okay. You said percent yield as well? Percent yield is going to be a formula. We've actually done this in lab a few times, but with percent yield, we're going to do actual of experimental times 100%. How do we find the experimental yield of any chemical reaction? It's a limiting reactant. Okay, so in order to find an experimental yield, we have to do a limiting reactant problem. Do we vaguely remember how to do limiting reactants? No. So let's go with A plus B makes AB. Simple formula. Simple chemical formula or chemical reaction. Let's say that we are told that we start with 20 grams of A and 30 grams of B. What we're going to do is we're going to try to figure out how much of the product both of those things will actually create, right? And whichever one creates the least is the one that is the limiting reactant. So we go from grams to moles of each. We go from moles to moles. Then we go to grams. 3-step process times 2. Now, is this a little bit ringing a bell? I hope so. Whichever one comes out with the smallest product number is a limiting reactant. So let's say that 20 grams of A produces 10 grams of AB, and 30 grams of B produces 5 grams of AB. Which one is the limiting reactant? Think about the question before you answer. I'm asking you which of them is the limiting reactant. Yeah. So this guy is the limiting reactant. The amount that it produces is the experimental yield. Oops, sorry. Oh yeah, that's right. What it should produce is the experimental yield, also known as the theoretical yield. So a lot of times you'll see experimental replaced with theoretical. Okay. What else was in this chapter? Sorry, did I get all 3 of them, Gavin, or no?
Yeah.
Okay. Percent element and percent yield. All right, what else? There was molar masses. We feel pretty good about molar masses. Hands up. Thumbs up. Yeah? All right. What's the difference between a formula weight and a molar mass? Anybody remember? Yeah.
Isn't it formula weight the amount of weight like it has like in the formula, but like it's a specific thing?
Not quite. Nope. It's easier than that. Anybody else? Go ahead.
The unit is AMU?
Yep. Formula weight has a unit of AMU. Molar mass has a unit of grams per mole. Otherwise, they're identical. We calculate them the same way. Okay. One of them is the formula. So a formula weight is the mass of one of those particular compounds. A molar mass is the mass of a whole mole. All right. Avogadro's number, percent yield. Cool. That's chapter 3. Any other questions in chapter 3? Go ahead.
What is Avogadro's number?
Avogadro's number, what is the number? 6.022 times 10 to the 23rd. And that's the number of atoms in 1 mole. Kind of like a dozen is 12. Say again? 6.022 times 10 to the 23rd. And that's atoms in 1 mole. Okay, and we've been asking about that note card, right? You are going to be allowed a half sheet of paper on your final exam. That means I'm not providing a formula. I'm not providing you a formula sheet. You make it yourself. You put your formulas, you put your constants, you put any other pieces of information you want. Half sheet of paper. I will cut them in half and I'll hand them to you today. I don't want anybody having a bigger piece of paper than anyone else, and I don't want this to become a thing. So, half sheet of paper, all right? Let's switch to chapter 4, yes?
Can we just do one side of a full sheet paper instead of 2 sides of a full sheet paper?
Yeah, that makes a lot more sense. Let's do one side of a full sheet of paper. I'm going to look at the back. If you have anything written on the back, I will give you a 0 on your final exam.
Can we use black light?
Listen. You get to write on one side of a full sheet of paper. If you write on the back, I'm giving you a 0 on your final exam.
Can we use black lights? Can we use invisible ink? Is that an
No.
option?
Listen. I want everybody to pay attention because this will become a problem, I'm sure. If you write on the back side of the sheet of paper, what's the score on the final exam?
0.
0? Did I hear 0? What?
1, 0, 0.
Like
Yes.
0.
Actually, no.
0 out of 100 is the answer.
0.
I'm going to give you a piece of paper.
Dude, I'm just gonna cut it in half just so I'm safe. But I'm not gonna mess this up.
Like sometimes I wonder, but you know what formulas are. You know what they are.
I'm gonna figure out formula, it's just gonna.
Can we bring magnifying glasses? Is that
I
an
would give you
option?
every formula from every chapter. I would not give you just the ones you need.
Can we bring magnifying glasses?
I'm gonna organize it. I know formulas are in a different. I'm gonna have a mental break.
But they're right.
I'm not taking kids.
In point or one font.
Right on the other side.
But you would be on
I
zero.
You give them an inch, they take a mile. Olivia.
Oh, you gave me one.
Oh, did I?
I mean, I'll take it.
You can use the whole side. Remember, so we're gonna do
I'm
one.
not taking a chance.
Wait, does it have to be handwritten? Does
What is it?
it have to be handwritten?
Yes. Yes, they have to be handwritten. That's a good
So
question.
we can't write in like one font in Microsoft?
No. I'm gonna say this for you too. One side of a sheet of paper. All right. Chapter 4.
That's gonna be the size of all my equations.
Let us begin. Please, thank you. Chapter 4 is on aqueous solutions. Woo.
I missed those. Those were my favorite.
All right.
So interesting.
We start chapter 4 with a definition.
The Webster Dictionary defines
Defines a solution as
I defined it as
yeah, long time ago.
Okay.
I promise.
I don't remember that far back.
you might have dementia.
All right, aqueous solutions. A solution has two parts. The solvent and the solute. The solvent is the larger part. The solute is the smaller part. It's the most common solvent. Okay? When you have a solute dissolved in water, we get an aqueous solution. For the most part, our aqueous solutions tend to be salts dissolved in water. Salt meaning an ionic compound that can break apart into two parts. From there, we had an electrolyte and a non-electrolyte. Electrolytes are ionic compounds in water. They conduct electricity. That's what the plants create. Sorry, do you understand that reference?
No.
Idiocracy. Anybody ever seen Idiocracy? Ridiculous movie from 90 something. Highly recommend. Like, how old am I? Do not conduct electricity. It's been like a month since I've written on a board. My handwriting is atrocious. It was bad before, but. So do not conduct electricity. Non-ionic compounds, think like sugar, when it dissolves in water, would not conduct electricity because it'll just stay as little sugar particles. It does not break apart into ions. When ionic compounds hit water, they'll break apart into their cation and anion parts, and that means that there are places for electrons to be attracted to, which means electricity is going to be able to be conducted through those electrolyte compounds. That being said, there are weak and strong electrolytes. This chapter doesn't talk a ton about how to determine the difference between the two. All it says is that there is such a thing as a weak and a strong electrolyte. We introduced acids in this chapter when we talked about weak and strong electrolytes. Thank you. Ooh. we see acetic acid, pretty famous weak acid. It's a weak acid because we've defined it that way. We talk a lot about this next semester and how to determine weak versus strong acids. But for now, what you need to know is that a weak acid will still decompose into a positive and a negative ion. We introduced the idea that acids have protons, which are those H pluses, and then they have their neighboring negative charges, whatever those typically are. We refer to them as weak bases or conjugate bases, if you will. This chapter introduced acids and bases in a kind of a very, very lame way. Just kind of defined acids and bases here. Yes?
Do you need to know like the 7 strong acids?
You need to know if you're given a strong acid, but the most common ones we'll talk about. You won't see like the chlorates or the chlorides. Yeah.
Okay, how do you determine if it's an acid or base?
Yeah, we're going to do that too. That's in this chapter, so we're going over that now. That was all the beginning. Aqueous stuff. Ooh. And this was, of course, the precipitation reactions. So we're going to do this first. We'll do precipitation reactions, and then we'll do acid-bases. Because those were the big topics in this chapter. All right, precipitation reactions use the solubility rules. You remember the solubility rules?
Of course not.
Do you have a vague recollection of the solubility rules altogether? I will give you the table. I will give you the table if I ask you questions about precipitation reactions. All right, so precipitation reactions were reactions that combine two aqueous substances to produce one aqueous substance and a solid precipitate. An example. All right, hopefully you remember the one rule that I'm aiming at here. One of these compounds is always soluble. What is it? A nitrate. This guy's always soluble, which means this one's always soluble, which makes this the solid. But how did we know that the nitrates were soluble? We used the table from chapter 4. Don't forget that that was definitely something we did. And in predicting our precipitation reactions, what was the next thing we did with those precipitation reactions? Do you remember? Say again? I can't hear, I'm sorry.
No, I think I'm ahead of myself.
Okay.
Yeah,
We're going to do the crossout thing called net ionic equations, remember? So we're going to separate everything first. Here, magnesium is going to separate into these two things. Are they aqueous, both? Yes, they are. We're going to separate the sodium hydroxide. Do we separate the O and the H? Heck no. That's a polyatomic ion. Let's keep it together. Again, are they all aqueous? Don't forget that. All right, now we're on the right side. We separate this guy?
No, it's solid.
Oh, no.
It's a solid. We do not separate the solids. We separate this one?
Yes.
I think I'm supposed to have a 2 here. Don't forget the little AQ symbols. Now what? Cross the stuff off that's on both sides. That's identical on both sides. whatever's left over is your net ionic equation. How are you feeling about it? Feel like there are some cobwebs?
Yeah.
Yeah, I know. I've been gone for a while too. That doesn't help. Doesn't help that you've been on a different schedule for the last few weeks. I'm aware. We're doing as much as we can. I'm here after school if you need me, most days. I might be busy for a few minutes, but I will definitely be here in the building as late as I usually am, if not later, because I have to write final exams this week. Yay. Okay? Yes? Canvas. If you're not giving a project-based final, we were told we have to put it on Canvas. Well, and your guys' is on Thursday, so. Yeah, but then you won't have this final next week.
That is so true. Because then I won't stress.
You get a whole day off next week.
And then I can
Wait,
sleep.
what?
Yeah.
Because you don't have to come on Tuesday.
Have finals on Thursday.
No, I don't like.
Can I erase?
Canvas.
We good?
Yeah.
Feeling good? Okay.
That would be the day that we have finals for this class, but we're taking
Precipitations. Acid bases. Here we go.
Wait, Michelle?
Yep.
What happens if we have computer troubles for the final?
You're going to be in the room. I don't know what to tell you. Don't have computer troubles for the final.
I'll try really hard not to.
Please bring a charged computer to class on Thursday. Thank you. Yeah.
I know how like we had like the for our exams it was like the short answer like writing part and then multiple choice.
All online.
So with like the short answer stuff, were you just like typing that in?
Yeah, so what you'll have is you'll be given a piece of paper to write your answers on, and you'll turn them in as like showing your work.
Okay.
Does that make sense?
Yeah. Okay. I was just
But it all goes into the system.
okay.
All right. Here we go.
Remember, just one side.
Okay, here we go. Acids and bases. The acid was defined as the proton donor. I will remind you that there were multiple definitions for acids and bases in this chapter. I care about the Bronsted-Lowry definition. You care about the Bronsted-Lowry definition. I care about the Bronsted-Lowry. You care about the Bronsted-Lowry. Hint, hint. What was a base defined as?
Proton acceptor.
A proton acceptor. All right, so over here we have two substances. Do they both have protons in them?
Yes.
Yes, they do, but is technically one of them not actually a proton? One of them is a polyatomic ion. The other is a proton on its own. So, which of these two is going to be defined as the acid? The HCl. Proton donor, also known as the acid. The other thing is then the proton acceptor. For us, if you don't remember, oxygen, typically when it's present in compounds, has two places where there are lone pairs present. Okay, whenever you draw out your Lewis structures that include oxygen, oxygen likes to have two lone pairs and two bonds. Lone pairs means place for proton to attach. Okay? So, if you're wondering which one is the proton acceptor, try drawing the Lewis structure. Okay? That may help you. You see lone pairs, that's probably going to be your base. All right, next thing, on the right. Over here, we have the most common products of what we call an acid-base neutralization reaction. Remember that was one of the buzzwords that we described these as. It takes a strong acid and a strong base and creates neutral products that have no pH. That's why it's referred to as a neutralization reaction. One of the products is always water, one of the products is a salt. Salt meaning ionic compound, whatever's left over. All right, from there, strong acids. If it is not one of the strong acids, it is by definition a weak acid or a base. What are the strong acids, you may ask?
Yes, what are the strong acids?
The ones you see most commonly? Nitric acid and, of course, sulfuric acid. These guys are the strong acids. There are two more. They're the chlorate, perchloric, and chloric acids. Very rarely do we use them in our situation. Yeah.
So if it leads with an H in that situation, it's most likely an acid.
Yes, that's a very good way to determine if something is an acid. If it starts with an H, it's probably an acid.
That's fair.
Problem is that a lot of times your book does this for acetic acid. It adds the proton at the end of the acetate ion instead of putting it out front.
I would only
So that's one of the ones to kind of be wary of. That guy, weak or strong?
weak.
Weak. It's not on my list of strong acids, so it must be a weak acid.
Why don't they just do the
Because what they're doing here is they're indicating where the hydrogen binds. By putting it there, what we're saying is this happens in the structure. A lot of formulas in your book do this on purpose to kind of give you an idea of where things are binding and how they bind. Say again?
So would it be wrong if I wrote it as CH4CO2?
No, it would still be the same. You just have to make sure you remember that that's one of the ways to write that acid. There are so many formulas for acetic acid, it's kind of funny. All right. Strong bases. Ooh.
Running out of space.
Running out of space. We're only in chapter 4.
Well, look at how much space I have for chapter 4. I don't have that much space to begin
I
with.
don't know what to tell you. Group 1A. Metal hydroxides. Those are some of the strong acids. And then heavy, group 2A, metal hydroxides. Etc. Okay. Ooh, I got 5 more minutes. Ooh, redox reactions. I would give you the activity series, just like I would give you the solubility table for this chapter. Please don't add those to your things, because you copying down the solubility series and the activity series is kind of a useless endeavor. Just like I don't want you to copy down the periodic table. I would give you those 2 things, just so you were aware. Given! You'll remember that from your Canvas quiz on this chapter, you were given these different things for the problems that you needed it. Yes?
Can we bring in the periodic table, or are they going to be given?
No, they would just be the ones I'd give you, like the laminated ones. Okay. Reduction oxidation. Remember mnemonic. Oil means oxidation is loss of electrons. I like to add the electrons at the end of electrons. Reduction is gain. oxidation reactions are two-step. First one is will it react? Second is what is reduced / what is gained. Oops, oxidized. All right, let's do an example. Or 12. Okay, what major concept did we have to know in order to do this? Yes. Oxidation numbers. All right, so how do we determine oxidation numbers of things that are in their elemental forms? What do we assume? 0. If it's in its elemental form, it has a charge of 0. Over here is something in its elemental form. What? Cool, 2 down, several to go. Over here, one of these is going to be positive, one of these is going to be negative. Which one's which?
Positive.
Nice. Why?
Because, yeah, good question.
I'm looking for one major topic.
Actually,
Starts with an E.
electrons.
Electronegativity is the answer. Chlorine is more electronegative than hydrogen in this particular case. But do remember that hydrogen can also be a negative charge depending on what it is. If it's acting as a metal, it's positive. If it's acting as a non-metal, it can be negative. All right, over here on the right. Nickel is going to be what charge?
+2. 2.
Wow, guys. Okay, nickel is a metal. Metals are typically positive, right? Chlorine is a non-metal. Non-metals are typically negative. What's the charge on a chlorine? -1. Chlorine is not something we're going to examine in this problem because it stays the same on both sides. We only look at metals when we talk about oxidation numbers for now. Okay? All right, nickel goes from 0 to +2. Did it lose or gain electrons? It lost electrons, which means it was oxidized. Hydrogen went from a +1 down to a 0. Did it lose or gain electrons? It gained an electron, which means it was reduced. Oh boy. All right, let's talk about the activity series. The activity series is that thing that starts with with elements at the bottom, moving up towards the top. Lithium is at the very top. Gold is at the very bottom. The things on the bottom are not very easily reduced. The things at the top are easily reduced. So, in order to determine this, any metal on the list in its elemental form can be oxidized by elements below it. So first thing we're going to do is locate the thing on the left that is in its elemental form. Then we're going to locate the thing doing the oxidizing to it, which is going to be the hydrogen atom. On my activity series, I've got nickel above hydrogen, which means, will this occur? Yes, so this thing needs to be above the thing that's actually oxidizing it. Correct.
Wait, say that again?
The elemental metal has to be above the thing that's being reduced, or the thing that's oxidizing it, if you will.
Ni is over.
This must be higher. See you tomorrow. Look over chapters 5 through 9 tonight. Circle what you need.
You don't need to do all of it, I promise.
It's gonna be okay then.
Spend some time with your book and you won't need to do all of it.
No, but I know I told her.
I know you know how to do it. You just gotta really buckle.
But you know what else?
Can we photocopy our notebooks and just put it into tiny windows on our paper?
Why?
Just to,
We should do a
make the paper.
We should do a conclusion first.
And just think we would be getting done with it.
What are we gonna do Wednesday and 11? For like those of us
You know what we should do on
who
Thursday?
while you were
Back to-
at home. What are we gonna do Thursday? Oh my god, I have done my finals work.
How about it's a Wednesday?
Yeah, that's the day before our exam.
You're still gonna class.
My cause of death almost
Yeah,
like
it's just a, it's like a late
blunt
start.
force trauma to my
So
head.
you're still gonna have like a 35 or 40 minute class, Emily. Yeah. Goodbye, have a great day. It's nice to see you again. Welcome back.
Yeah, because it was supposed to be today. And then I freaked out because I thought that I wasn't gonna get to review before our exam.
Review of that. I like your face shield. It's cute.
It's really hard to wear it with reading glasses.
Yeah.
I can't pull it.
There's a lot going on. Yeah.
Right. So you see over the
I didn't take that.
Yes, yes, yes.
What if I've never seen it?
I know. We can like,
I've just
we're like, what the heck?
taken it during this week's
Oh my.
Daily Q.
I'm like,